We're going to go ahead and do a video here on mechanics, our introduction to it. And by that, I mean what we're going to be doing is our first step in kinematics. And specifically, one-dimensional kinematics. So this is going to be restricted to basically what this means. Kinematics is just the study of how things move without worrying about what's causing them to move. So we don't care if a rocket's engine is making it move or somebody's hand is pushing it. We're just worried about the actual motion itself. And then one-dimensional means basically everything in just a straight line. We're not worrying about going up and down and left and right. We're only going just either left or right or up or down, like we're on a train track and all we can do is move forward and backwards. Later on we'll get into two-dimensional kind of motion, which can then be extended to three-dimensional motion pretty easily, but for now we're going to start with just this one-dimensional motion. So the first thing we need to do is define what a frame of reference is. Okay, frame of reference. So essentially this is basically just the coordinate system that you're going to use. It's the coordinate system that you're using to make your measurements. And when I say coordinate system, I mean like the old coordinate XY coordinate system that you used in math class. So it's different for everybody because where I'm sitting right now is different from where you're sitting. So where I'm sitting right now, I would say, okay, I'm sitting here at my desk. This is my coordinate system right here. I'd say that's Y, that's X, and this would be my coordinate system. But you're sitting off somewhere else, and you could be sitting in the opposite direction of me, in which case this would be Y and this would be X. Okay, or somebody else could even be at some strange angle or something, and they could be their Y, and that could be their X. And so basically, it just depends where you are. You could even have someone who's got this coordinate system, say this is their coordinate system, and they're driving or moving in this direction. So their coordinate system is actually moving. And that's originally what started all of this, was the Galilean transformations, and it was a way to allow you to say, all right, I'm sitting here and I'm looking and this is my coordinate system, and I'm sitting right here at the origin of my coordinate system, and I want to know what do things look like for this guy I see, going by me on a horse or something, going at this speed. What if I saw something happening over here, like say at this coordinate system, I'd get my XY coordinates at that spot. What would it look like to this guy? Or even vice versa, I could say, where is this guy's origin as he moves through my coordinate system? So he may start here where he's at like, +8, -3 or something, and then a short while later he's at, +3, -10 because he's moved over here and his coordinate system is over here now as he moves. And those were called the Galilean transformations, and it was a way to move between these coordinate systems and kind of see either where coordinates would end up or how things would look to people in other coordinate systems where they would say things happen, because it's all different. And so what we're going to do is we're going to pick a specific coordinate system, usually our own coordinate system, the one oriented the way we're used to, with y being up or forwards and x being, the left and right type thing. But we're going to restrict it just to the xy axis, due to one-dimensional now. Later we'll do two dimensions. And we're going to pick that frame of reference, that coordinate system that we're going to use, and we're going to make measurements and do all kinds of things inside that one frame of reference. All right? So let's start with defining some things. The first thing I want to define is displacement. Displacement. We've talked a little bit about this, I believe, when learning about just vectors, but displacement, this is measured in meters, the SI unit. So SI unit is the meter, which is just that lowercase m. So that's our unit we measure it in. And we're going to define this as displacement is, remember this delta means change in. So it's a change in our x position. We're only worried about where we are on this x-axis. Change in x, that's our displacement. That's our definition of it. And anytime you see this triangle, that means that's a Greek letter delta, and it means change in. So it would be our final position minus our initial position. All right, and that's all that there is to that. That's this change in always means final minus initial, so it means final position minus initial positions. So if we have some coordinate system, shouldn't have made the vertical line. So let's say we have some coordinate system here, some axis, some x-axis, and we look at it here. This could be 0, and then 1, 2, 3, 4, and -1, -2, -3, -4, so something like that. 4, -4. You could start at, say, -2, and this would be x initial, and end up at +3, that would be x final. And so you'd say that your displacement then is +3 minus +3 minus -2, your initial position, and that gives you then, of course, a 5 for displacement of whatever unit this happens to be, 5 units. And that would be your displacement. It's just the straight line of where you started to where you ended up. Notice I said nothing about where you went in between these two. I just said your initial and your final. I didn't worry at all about what path you actually took. You could have started here, gone back to -4, up to 0, back to -1, back up to 4, and back down to 3. I mean, it doesn't really matter. All that matters is your initial and final positions for displacement. That makes this a bit different than just regular old distance. Distance would basically be how many steps did you take. So if I started here, then I took 2 steps back, and then I took a bunch of steps forward, and another step back, and I'd add up every step I took. And that would give me the total distance I traveled. But for displacement, I'm only worried about how far I am from where I started. And hopefully you're thinking that sounds kind of familiar, because it should sound a lot like how we defined the resultant of something. It's basically how we defined a vector, where you started to where you ended. So this distance, which is just how many steps you took, is a scalar. Okay? But our displacement, which is just how far you are from where you started to where you ended, is a vector. So they're very similar. They are both measured in meters, but one is a scalar and the other is a vector. And so that makes for some pretty big distance differences between them, and you have to be careful. Sometimes the distance is the same as the displacement, but other times, like in my example here, where I walked backwards and forwards and backwards and forward and back and everything, the displacement and the distance are different. Had I just walked straight from x1 to x final, or x initial to x final, then my displacement and distance would be the same, except displacement would have a direction and distance wouldn't, but their lengths would be the same. But other than that, they're not the same. So think about NASCAR. You're race car driving, and I don't really care if it's a circle track or one of the road crazy tracks, but let's just pretend we're talking about the oval tracks. Now, they start here, and they drive around. And so I think you could think of something like the Indianapolis 500, where I believe they drive 500 miles. And so they go around the track a whole bunch of times. And by the end, their distance, the distance they've traveled, is going to be something like 500 miles. But their displacement, if you look at where they started and where they ended, their displacement would be 0. Because they haven't actually gone anywhere by the end of the race. At the end of the race, their displacement is just 0. They're right back where they started, and so their displacement would be 0. So basically, the guy who wins a NASCAR race is whoever does nothing the fastest, because ultimately they've done nothing. They're right back where they started. So spend some time thinking about that, this distance displacement kind of thing, and be careful about it. And remember that displacement being a vector means you not only have to tell a a distance that you went, a length, but you also have to tell a direction. So like this would be, for displacement, it would be whatever it was, 5 units to the right. That would be very different had this been the initial position and this been the final position, in which case it would be 5 to the left. And if you did this problem out, you would see, if you did the math, that would be -2 minus 3, and it would give you a -5. So that negative would tell you that it was in the opposite direction. It was pointed in the negative direction. So be sure to be very careful about that when it comes to displacement, to thinking about direction as well. So after displacement, which we get just simply from this, we can move on to that, and we can look at velocity. And velocity is very similar to speed, but it's a little different. The SI unit for velocity is a meter per second. All right, it's a distance over a time. And you should probably be used to this. You look at getting your car and you're going 60 miles per hour. It tells you how far you can travel in a certain amount of time. And that's our velocity. But this is a bit different from speed. Speed being the scalar version of it. Much like distance being the scalar version of displacement, speed is a scalar while velocity is a vector. That means velocity has not only a length, a size for how fast you're going, but it also has a direction. Speed, just a scalar, only tells you how fast you're going. So you have to be very careful about that and the difference between them. So I could tell you something like, I'm traveling at 60 miles per hour. Well, that's great. You still have no idea where I'm going. I could be going at 60 miles per hour in a circle or oval, or I could be going in a zigzag, or I could be going in a swirly pattern, or a spiral, or in just a straight line as well. I could be doing whatever I want. I could be going forward and backwards and forward and flip-flopping back and forth. That's just speed. It's basically whatever the little speedometer on your car tells you how fast you're going. You could be turning a corner and all kinds of stuff. Velocity, on the other hand, would be like if I told you I was going 60 miles per hour north. Now suddenly I have a direction and it becomes a vector, and it looks like an arrow, just like the stuff before. Okay? So be sure you can differentiate between speed and velocity. Unfortunately, the variable we use for both is pretty close, and what we're more is the same. It's just a little lowercase v. But what we're more interested in here at this level is something called average velocity. So this average velocity can be found like this, v, and put a little sub avg on there for average. So average velocity is equal to displacement, which was our delta x, over a change in time. Now, right now, I'm writing the delta in front of time. I will probably stop doing that because every time you have time, it's always change in time. There's never a time when you have time and it's not change in time. So I tend to get kind of lazy and I start writing it as just t, because it feels very redundant to constantly write a delta in front of it, since every time you have is always a change in time. So this would then be change in position x final minus x initial, that's our displacement, over time final minus time initial. And here's another reason we can always just leave off the delta, is because you pretty much always start, when you start your stopwatch, you usually start it at 0. You reset it and you start timing at 0, so that's always 0, and it's just, you just read off how long it took for something to happen from your stopwatch. But this right here, this is our main equation for velocity, and you can see that you would look at how far you were from where you started and how long it took you. So if we went back to our NASCAR example, it would be however many hours later, and their displacement would be 0, and their time would be however many hours it was, and you'd have 0 divided by 3 or 4 hours, and their average velocity at the end of the race is 0, much like their displacement was 0. but that's not always the case. Their average speed would be something around whatever it is they go, 200 miles per hour. It's going to be less than that because they have times where they have to slow down for accidents and everything like that. But their average speed is going to probably be more like 150 miles an hour because that's not worried about them. It's not worrying about their actual displacement. It's worried just about how fast they were going the whole time, what their speedometer read. Whereas velocity here, that I've written here, is only worried about where they started, where they ended, and how long it took them to do it, not anything about what they did in between. Okay? So that's average velocity and velocity in particular. And displacement, remember these are both vectors. Their displacement is different from distance, which is the scalar, and velocity is different from speed, which is the scalar. Velocity is typically speed with a direction. Okay? Now there's one more little thing we have to go over here, the last little bit for this, and that is acceleration. Acceleration. Now acceleration, I'll tell you the SI unit for this, is a meter per second squared. And in a moment I'll explain when we do the equation for this where this meter per second squared, where does that even come from, and a better way to think of it than just that. What we are mostly interested in, and pretty much the only thing we will be doing, is constant acceleration. At this level, we're not doing anything but constant acceleration. We're not worried about changing accelerations or anything like that. That gets too complicated. But we're doing constant acceleration. And this is also, you probably guessed it, a vector. It has a direction. You could be accelerating in the positive direction or the negative direction. This also brings me to, you may hear some people say something is decelerating when it's slowing down. We in physics don't really like to use the term decelerate. What you would say is something more like it is a negative acceleration. Okay, but even then that's not always necessarily true, and we're going to go over a chart in a minute about that, dealing with positive and negative accelerations and velocities and displacements. But there's no deceleration. It's always just acceleration. The acceleration can either be speeding it up or slowing it down, and that just depends on the sign of the acceleration compared to the sign of the velocity. And I'll get back to talking about that in a minute. So again, we only want to talk about this constant acceleration, and we can come up with our nice little equation over here for acceleration, and it is simply the change in velocity per time. Okay? Change in velocity per change in time. That's v final minus v initial over time. And so that's our main equation right there. That's basically our definition for acceleration. Change in velocity over time. Now we have two of these over time things, per time. Right? I can put the delta there for now. We have change in position or displacement per time, and we have change in velocity per time. And basically every time we have this per time kind of thing, divided by time, we're going to basically just call it rate of change of. So I'm going to put that right here. So we're going to do rate of change of something, and that just basically means divide by time. So the rate of change of position would be velocity, and the rate of change of velocity would be acceleration. Okay, so just kind of keep that in mind. Whenever you hear that rate of change of, it means you're just dividing by time. Now, going back to this acceleration. Now, what does this mean, and more particular, how do you think about these units? Well, this is essentially telling you how quickly your speed is changing. Much like this tells you how quickly your position is changing. And so if you think about this, this unit on the top here, this velocity part, if we just look at units, is a meter per second. Okay? Because that's what our velocity is in. And then this time is measured in seconds. And if we look at that, that's a meter per second times a 1 over a second. And what does that give you? It gives you a meter per second squared. So it's shorter to just say meter per second squared, But in your head, you need to be thinking of it more as meter per second. Okay? And let's give an example. Let's say you started, your initial velocity is 0 meters per second. And then your acceleration, let's say we don't know what our final velocity is. Okay? Your acceleration is, let's call it 2 meters per second squared, or 2 meters per second per second. And I want to know, how fast are you going after 4 seconds? So we could go back up here and we could use this equation, and we could use this part of it out here and try and isolate VF, and we'll do that in a second, but let's just think about it for a second. Acceleration tells us that with this positive acceleration that we are increasing our speed by 2 meters per second. I'm going to write this off to the side. 2 meters per second every second. That means after the first second that goes by, one of our first 4 seconds, we started at 0, we have to add 2 meters per second onto it. So after 1 second, our speed should be 2 meters per second. After 2 seconds, we add another 2 on, it becomes 4 meters per second. After 3 seconds, we've added another 2 meters per second, because that's what our acceleration is telling us. Add another 2, that's 6 meters per second. And after 4 seconds, which is what we're interested in, it becomes, add another 2 on, 8 meters per second. Now, this one's pretty easy because we have a whole number of seconds here, and it's not a very big number, and we can just keep adding 2, right? We started with 0 meters per second. Just add 2, add 2, add 2, add 2, and get our final answer here that after 4 seconds we'd be going 8 meters per second. But what if this is a decimal number? What if it was like 4.375? Or what if it was really big and we don't want to sit here and do 2, 2, 2, 2, 2, 2 a whole bunch of times, because it might be 250 seconds or 2 million seconds. We're going to sit there adding up 2's the whole time. So that's where we can fall back and use this equation. So let's look at this. We say we have acceleration equals change in velocity over time, which is v final minus v initial over our time, the amount of time that goes by. And now we want to solve for v final. Okay? So I want to go ahead and isolate this. I'm going to multiply both sides by time to get time out of the denominator, because I want to isolate this v final. That cancels that. And so then I have, we're just switching their sides, v final minus v initial equals acceleration times time. That's the same thing. I just moved this to that side and that over to the other side. Okay? And give myself a little more room there. Now, if I want to get v final by itself, I just have to add v initial to both sides, right? Just regular old algebra here. That'll cancel it out on this side, and I'll have v final equals acceleration times time plus v initial. And then all I have to do is plug my numbers in. My acceleration is 2, oops, make that a little bigger. My acceleration is 2 meters per second squared, meters per second, every second, per second, so meters per second, and then my time is 4 seconds, and then my initial velocity is 0 meters per second. And this would be 2 times 4 gives me 8, and I have a meter per second squared times a second, which means this is in the numerator, and it cancels with one of the seconds in the bottom and leaves me with meters per second, which is the unit I would expect for velocity, and I get that same answer that we got up here. And you may also want to think about this, well, what if we hadn't started at 0? What if we had started at 4 meters per second, right? If we had started at 4 meters per second, we would have done plus 2, 6, 8, 10, 12 we would have come up with, right? And look at this equation down here. If I went down here just to this part, and instead of starting at 0, I started at 4, I'd end up with 4 plus 8, and I'd get 12 again. So this would have given me 12 if we had started at 4, and this would also still give me 12 if we started at 4. So they're consistent with each other. Except this equation, using the equation, is going to work very easily in all situations, whether you have decimals or huge numbers or whatever, this will work, and you'll just go through, use this equation here, and solve it. Okay? Um, so that's basically it for acceleration, and we'll do some more practice problems on that later. So I want to talk to you about that, go back to that whole deceleration thing. How do you know whether or not acceleration is speeding up or slowing down? So speeding up or slowing down. How do you know? And the answer is you basically have to look and see whether or not the acceleration and velocity are in the same direction. So if acceleration and velocity are in the same direction, then you're speeding up. Okay, that's speeding up. I didn't write that very well, but that's speeding up. The only other situation is if acceleration and velocity are in different or in opposite. Shouldn't just say different, let's make it opposite. Are in opposite directions, because when we get to two-dimensional motion, different won't necessarily mean opposite. In opposite directions, then you're slowing down. Because remember I talked about that positive and negative signs, they indicate direction. So really all you have to do is look and see, do they both have the same sign? This would mean they're both positives or they're both negatives. If that's the case, they're speeding up. But if one of them is positive and the other is negative, or vice versa, it doesn't really matter which one. The acceleration could be positive and the velocity could be negative, or the velocity could be positive and the acceleration could be negative. Whichever way it is, then it's slowing down. They're working against each other. So we could maybe make our a little chart here. So velocity, acceleration, and then we'll do this here. So if velocity is positive and acceleration is positive, we're speeding up. Okay? That's the first one. If velocity is positive and acceleration is negative, we're slowing down with a D, slowing down. Okay? Make these a little longer. If velocity is negative and acceleration is positive, they're opposites, it's slowing down. So maybe I should write down. Slowing down, here you're speeding up. And the last possibility is if they're both negative, that would make them the same, and this would be speeding up. It's just this would be speeding up in the negative direction. This would be speeding up in the positive direction. This would be slowing down but moving in the positive direction. And this would be slowing down but moving in the negative direction. But either way, you're going towards that zero speed. All right? Spend some time thinking about this and try and get all of this to reconcile in your head. Just remember that you have to pay attention to, one, your frame of reference, where your zero coordinate is set, displacement, vector, so it has a distance and a direction, length and a direction, and then distance is just a scalar, and then velocity is a vector as well, and it's got a counterpart scalar version called speed, and we use this equation for it. And then acceleration is a vector. We don't have a real scalar version of that, and it's got this equation here, and we're only worried about constant acceleration. We even did a problem out here doing it, a little one I made up a couple different ways. And then you need to remember how to tell if things are speeding up or slowing down based on how the velocity and acceleration signs are with each other. And so just add on that just to make sure this is in the, this slowing down, this is opposite directions. Opposite direction, because those negatives and positive tell direction. This is the same direction, right? And this one is also same direction, positive, positive. All right, so I think that's about all for now.